Welcome to the presentation. Before digital photography, developing pictures required the use of an enlarger where the negative was placed on the top of it. Different exposure times create different contrast on the developed images. When taking images, what can go wrong? Photography can be seen as painting, but the medium is light, and in this case, it's a very limited brush. In the darkroom, we sometimes can block the light partially, as it is shown in this image here, in order to obtain the results that we're looking for and obtain images like this. For digital images, we have pixel values as the ones shown there, just few pixels of that entire image. And the range goes from 0 to 255, and as you can see, values that are very close to 0 are dark, and values that are close to 255 are light. A histogram is formed by counting all the pixels for one particular value, as highlighted there, the ones with 14. Let us bring the nice image that we obtain with the enlarger and see what the PDF associated with that image is. As you can see here, we still have dark values as highlighted in this area here, but we in fact have more lighter values, even whites, in this one. So for example, pixels that landed in that region are mostly appearing in that peak on the histogram. A very popular technique to enhance the contrast of an image is histogram equalization. In this technique, we form a transformation function in which the pixel value with grade level value R of an original image is going to be transformed into a pixel value S. Let's say, for example, that we have a pixel of value 14 landed in that particular area of the image. Most likely than not, this transformation function is going to convert that value into something that is going to become lighter. The transformation needed to obtain this equalization can be formulated in the continuous case with that formula, which basically is telling us that that transformation function is just the CDF, or the cumulative density function of the probability density function associated with the original image. In the discrete case, that integral becomes that sum, where once again, PR is your original probability density function associated with the bad image that we would like to enhance the contrast. By using this technique, this is the result that we have. As we can see, we have really a lot of values of white, we no longer have those many pixel values of black, and we kind of have everything in between. And that's what histogram equalization tried to do, is spread those values in the histogram, the blue one, into the green one, hopefully from 0 to 255. Notice how, for this particular case, we don't have that perfect uniform distribution, which is the goal of histogram equalization. And one of the reasons is because when we do this transformation, there will be several values that have to land into a single one, and that creates this effect. Remember that a nice image, like the one we obtained from the darkroom techniques, the PDF looks like the one I'm showing you there. Even when employing techniques like exact histogram specification, that I will put the links down there, we obtain images like this. Notice that there was not a lot of change between the case of not having an ideal uniform distribution and this one. So let me go back to the previous one and bring the nice image obtained in the darkroom, and notice once again um, the probability density function associated with that image is P of Z. So now what we need to do figure out a technique that can change from the original dark image on the left an image that comes closer to the one further to the right. For histogram specification, we will start by doing histogram equalization of our original image as it is indicated there. And let's assume at this point that we actually have available a nice image in terms of its contrast and its probability density function P of Z. The idea here is that if we apply histogram equalization to this nice image, the final histogram that we will obtain is uniform as the same as the one on the left. So because of this, we can equate those two expressions. So S on the left is equal to S on the right. Great implementation of histogram specification, those integrals become those two sums. And once again, what we have there is the cumulative density function of the image on the left equated to the cumulative density function of the image on the right. What we're going to end up in the implementation is to have those two lookup tables corresponding to those two CDFs, and I'm just plotting them as you can see there. So for example, for a pixel level 14, the histogram equalization would tell me that that 14 needs to be changing for the original image to a value of 42, as we can see on the table. Now I need to see what that 42 lands on the other lookup table for the CDF associated with the nice image. And I'm going to find out that that value lands in there. So 35 according to the lookup table. So as you can see here, that dark pixel with value 14 was changed to 35, and that will tend to lighten that area. The image you see in this slide corresponds to an image that has been underexposed during taking it and overexposed one step while developing. On the right, you have the histogram of this original image on the blue, and on the green is a desired histogram where the effects that we're looking for is to eliminate the granularity of the image. And these are the results. So with this example, we can see that histogram specification can deal with problems like this. There are different techniques proposed in order to specify a histogram that hopefully will yield a nice contrast image. One of them is brightness preserving histogram equalization, and this technique yields a final result, a final image with a similar brightness level as the original one. In order to accomplish this, the specified histogram f of z obtained maximizes the entropy and is subject to the constraint that the average level of the final image is the same as the original one. The idea here is that if an image is dark at the beginning, the better image is not necessarily one that will turn the complete image into a brighter one, or vice versa. For example, let's start with that image. As you can see, it's darker than what we would like to have, and we can see that by computing the average value, which is equal to 0.28, and highlighted in yellow are two areas inside the closet and the person on the left, which appear to be darker and we miss some detail. If we apply regular histogram equalization, it will expand those values. We will have whites and blacks and everything in between, but notice the average value of that image is 0.499, which is not necessarily what we would like to have. So let's bring those two images again on the top and use the technique that we previously discussed. And these are the results. As you can see, the histogram that is specified on the green is not necessarily the uniform. It maximizes the entropy and keeps the original average value of the image. So in the center you have the result from this technique, and that's actually the original value of the mean. And as you can see, it's very close. So this forces the image to have the same level of brightness overall, but it tends to highlight in less dramatic ways than histogram equalization areas that lost contrast. A couple of other techniques that can help us to identify a final histogram that will lead to a better image are contrast enhancement by piecewise linear transformation, or PLT for short, as well as piecewise maximum entropy. The idea here is that as we start with an original histogram corresponding to an image with not a very good contrast, we would like to avoid using histogram equalization that will tend to give us a final image with a uniform histogram like that. The idea here is that to extend the pixel values within regions of the histogram. Notice that we divided that histogram within sections where between two valleys of the histogram, we will define a section. And the idea is to extend those pixels between these gray level values, for example, in the yellow area, in such a way similar to histogram equalization, so they will turn flat or uniform within those sections. Now, when we use such a technique, these are the results that we obtain with the example that we've been using so far. So notice how between these valleys here, we are changing the histogram from that peak to one that is uniform within that area. Similarly, within those valleys, instead of you going flat in the response of the histogram, we can use the maximum entropy approach. And this is the result that we obtain. And as before, the grade level value, the mean value of the grade level values between that section will remain the same using PME. Histogram specification can be used to help us segment images. Let's take a look at that image where we're trying to segment those parts. So the segmentation is the one in blue, and notice how we're missing some parts on the image. These are the histograms corresponding to the original image in blue, as you can see there. Between the peaks, we don't have a clear valley, so any thresholding technique that will allow us to identify those segments is not as clear in the blue as in the green. So the idea is here to obtain an image with a histogram specified as the green one, where we can see two peaks. So there's actually two Gaussians located where the original peaks are, and the modification to the image is like the one I'm showing you on the right. And notice how the segmentation is improved. Further details of the different techniques discussed here can be found in that reference. For example, you can find more details on the maximum entropy approach on the left, or you can find more details on the contrast enhancements by PLT, as indicated on the right, as well as more examples dealing with segmentation and image enhancement. Thank you for listening.